So last time you saw me, I introduced you to a bunch of different kinds of measures in 3D. Arc length measure, volume, area, surface. Before I can really make those things pop and give you context for them, I need to step all the way back to vectors. It's kind of like we did this circular thing and we've gone all the way back to the beginning. Except for now I'm going to be talking about a vector field. Now, as you can imagine, I'm going to limit myself with drawing 2D vector fields because 3D is not my forte. Vector fields are vector valued functions. It's not new. Just the notation that we're using and the word we just use, vector field, as opposed to vector valued function, because there's going to be a purpose to what we're doing. Promise. So a vector field will often be denoted by a capital F with a little half arrow thingy over top to indicate that I am getting a vector. And the I component will be denoted by a function M, capital M. The J component will be denoted by a capital N. When we're in 3D, then the I component is again denoted by a function named capital M. The J component is again denoted by a function named capital N. But the K component skips down to capital P because we don't want to use an O because it looks like origin and zero vectors and all of that and gets confusing. The way we draw a vector field is slightly different than the way we draw a vector valued function. In that, whatever point in the domain of M and N, or M, N, and P, that we plug into our vector field, that's going to be our initial point of any vector that we get out. Okay? So, big M and little n in 2D, each of them might have a different domain. I can only use points that are in the domains of both functions. Plug in those points, I will get out a vector. And then how I draw that vector will be to use the point I plugged in from the collective domains of M and N as the initial point. And then I draw the vector that I get out using that as an initial point. So the concept of displacement is going to come into play. So here's an example of a vector field, a simple one. I think everyone that does this uses the same 2D vector field as its starting example. Minus yi plus xj. Well, y minus y is my m. So here, mxy is just minus y. X times j, so if I'm keeping track of notation, big N as a function is just x. Not very exciting until we draw it. Both M and N have the entire plane as their domain. These are two-dimensional functions. Their domains are subsets of the plane, and all points in the plane are fine being plugged into this big M and this big N. So when I plug in 1, 1 to my vector value function, I'm going to get minus 1i plus 1j. minus 1i plus 1j. When I plug in minus 1, 1 as my point, I get minus y, which is minus 1, plus negative 1, j. So I get the vector minus I minus j. Bet you can guess what's going to happen when I do minus 1, minus 1. Plug in minus 1 for x, minus 1 for y. When I do that, I get 1i and minus 1j. 1 negative 1, 1 for x minus 1 for y, minus 1 for y right there, becomes I. 1 for x there, becomes j. Now I'm going to finish this table. So now I've got another set of 4 points. You may ask how many points are enough. Who knows? You know, anytime you see something new that you're supposed to graph, you just pick some stuff to plug it in and see what you get out. I pick some stuff to plug in to see what I get out. And then after I draw some of these, I'm going to pick some more stuff in. I'm going to plug some more stuff in and get some more stuff out just for, well, for Paula reasons. So the point 1, 1 is in the domain of my vector value function. So I'm going to make this one and this one like that. So 1, 1 is in the domain of my function. And when I plug it into my function, I get out the vector minus I plus j. Now sometimes it helps to rewrite that in component form so you can see the displacement. I move 1 unit to the left and 1 unit up. 1 unit left, 1 unit up. From my initial point, 1, 1, I move 1 unit left, 1 unit up, draw a little arrow, and there is that vector. When I plug in minus 1, 1, I'm talking about that point. Pretend that these are straight. And what I get out of my vector value, what I get out of my vector field is minus 1, minus 1. So from here I go left 1, down 1. To find my terminal point. Now I'm going to keep drawing these vectors. I'm going to fill up the screen. All right, so I've drawn some more vectors. Drawn all the rest of my 2D vectors that I've plugged in, plus I threw in a couple extras. Just to demonstrate, the point minus 1, 2 is going to go to the vector minus 2i minus j, minus 2i minus 1j, which means when I'm at the point where x is negative 1 and y is 2, my displacement because of this vector field is going to push me 2 units to the left and 1 unit down. So 2 units left, 1 down. And then I completed all of the rest of these vectors. Drew them up here. I threw in 5 more. Let's think about the vectors. Let's think about the point 0, 0. If I plug in 0 for x and 0 for y, I'm going to get the 0 vector. So 0, 0, boom, is the 0 vector, which we just draw as a dot. And where are we going to draw that dot? At the point we plugged in as its initial point and terminal point, because it's the 0 vector. If I look at the point 1, 0, 1 for x, 0 for y, then I'm just going to get the vector j, which means starting at the point I plugged in as my initial point, I go up 1. If I think about the point 0, 1, 0 for x, 1 for y, that's going to give me the vector minus I. And so from 0, 1 is my initial point, I'm pushed left 1 unit. Now I know my picture's not drawn to scale, but when are they ever? Now you should notice that this vector field has some counterclockwise action going on here, okay? And how many points you plug in, how many vectors you get out and decide to draw is entirely up to you. We have software that draws great vector fields for us. We say, okay, I want to see 100 vectors. I'm not drawing 100 vectors, but draw enough vectors to get a good idea about what the vector field is doing. Now, why would I talk about vector fields? What is a vector field? What is a field in this context? You ever stood outside on a windy day? Maybe flown a kite on a windy day. The path of the wind is governed by all kinds of things. Rotation of the earth, revolution of the earth, the jet stream, the Gulf Stream, Santa Ana winds, all kinds of different things depending upon where you are geographically on the planet when you try to fly your kite. The kite is pushed according to the way the wind is blowing. If you need to see another vector field, next time you take a shower or a bath, watch the water running down the drain. When the water's running down the drain, doesn't it start to spin? If you watch that water going down the drain after a bath or during a shower, actually probably a bath is better because with a shower it runs out pretty fast. Okay. But the path of that water is governed by gravity as a force, which is pulling on it, the slant of the bathtub or the floor of the shower to make sure that the water drains into the drain. They create a vector field. If you're feeling energetic and you're not worried about the cleanup afterwards, put some water in a bathtub, take a bath, do whatever, and right before you let the water out, just drop some food coloring in a color that you can see, and then let the water out. And then you can watch the flow of the water a little bit better. So I mentioned that this particular vector field has got some counterclockwise turn to it. In physics, we say that this vector field has curl, C-U-R-L. Tornadoes, hurricanes, typhoons, dust devils, they all have curl. They're also governed by vector fields, making them spin. Some things don't have curl. When you're watching water go down a stream, maybe off a waterfall, you don't see any twisting around. Water just falls. It's falling because of gravity. And the way that it falls has to do with the shape of what it's falling over. And it just falls. So there may not be any curl. We're going to take a look at some different aspects of these vector fields. Rather than asking you to draw a bunch of vector fields, I'll just show you some images of vector fields when we need them. You're probably wondering, where'd chapter 17 go? I'm weaving it into chapter 18. So that all those measures that I showed you and all the different kinds of integrals that we'll do will have a context.